to the 29 lecture organized by Tibet House in collaboration with India International Center. Before we proceed with today's lecture, I would like to request Professor Nicolas Gisin and Mrs. Gisin to please come on the dais, and I would like to request our director to present them with the scarf and a memento as a gesture of appreciation. Yeah. Please welcome our guests with a big round of applause. I would now request our chairperson, Geshe Tojit Abdullah, to kindly take a seat. And our speaker for the evening, Professor Nicolas Gisin. Okay, so as I can see a lot of familiar faces here, and I'm sure everybody is aware that Tibet House regularly and almost every month tries to organize such lectures on various topics which has some relation with Buddhist philosophy at the same time. So this is one such event, and as I can see, almost everybody has the brochure in their hands, so we have our email address in the brochure, so please feel free to contact us so that we can send invitations in future if any such event occurs. So that would be a short notification in the beginning. So before we go further on this event, I would like to request Geshe Tojit Abdullah to please take the podium and say a few words on this event.
Okay, welcome you all to this program, the Department lecture, one of the most prestigious lectures and prestigious plus academic lectures to be organized by Tibet House. And the Padma means the lotus. Pani is the holding the lotus. So this signifies the holding compassion, manifesting compassion. And this lecture, while it is being the very academic, more on the academic side, and at the same time, the point is that it should not be deviated from compassion. It is for this reason that the title of this lecture, besides the specific title chosen by the respective scholars, the main title is the Padma lecture. So they're holding the lotus of compassion. Finally, the point is that with the advent of human beings on this earth, if you go back in the history of humanity, we see that the human thinking was very crude, very coarse, and simply the thought processes were all about the survival. Where to get food, where to get shelter, that was it. And then over time, the human thinking, the thought processes became more and more sophisticated. And then not only the food, shelter, and so forth, but the basic, the mental happiness. And in this pursuit, the thought process developed to the extent of now what we see as quantum physics, relativity theory, and neuroscience, and so forth. So the point is, if we we may get the impression that the quantum physicists, what do they have to do to contribute to the well-being of the humanity? And the neuroscientists, we do acknowledge that, this has a lot to do with the mind and the happiness of the mind, and so forth. But quantum physics, of course, as a very important branch of the human knowledge, it should have a great role to play for the well-being of the humanity. And particularly, they say that I'm very honored that I know Professor Ciceroy since as early as 2005. And you may be wondering how I came to know this great physicist, the Professor Ciceroy, before I met Professor Gisin. So how I met Professor Ciceroy was that, in fact, you may be wondering why I'm talking about Professor Ciceroy, because why we are being so fortunate to have met with such a world-renowned quantum physicist today was all because of this great Indian scientist, Professor Ciceroy. And how I came to know about him was that those days, 2004, 5, 6, I was working in the office of His Holiness the Dalai Lama. And then Professor Ciceroy, very innocently and very fortunately, he wrote a letter to His Holiness. Just the ordinary person. He had a physics question and he wanted to know this answer from His Holiness the Dalai Lama. See, he wrote to His Holiness about the relationship in the concept of continuum, concept of relation with the specific instances from the point of view of philosophy. So His Holiness the Dalai Lama. So those days I was the initial stage of being inclined towards the office, working there. Then the office of His Holiness directed a mail to me. Give answer to this scientist. So this is how we came to know each other, Professor Ciceroy. And then recently we were organizing a big conference on quantum physics, and Buddhist philosophy of Nagarjuna's philosophy of emptiness in Sikkim. So that is soon going to happen. So there, what happened was that I was seeking the help of Professor Ciceroy from Calcutta to recruit scientists. And he gave me the name Professor Nicolas Gisin. And then I just put Professor Nicolas as just a normal speaker. And Professor Ciceroy said that no. If you were to invite him, you must make him a keynote speaker. I said, why? He is a world-renowned quantum physicist. We cannot treat him like an ordinary person, an ordinary speaker, ordinary scientist. So this is what he said. And instantly we have to change the plan. And then we requested him to be the keynote speaker for the conference, which is soon going to be happening in Sikkim, organized by Sikkim government. So the point that I'm raising here is not my lecture, but to inform you that the person sitting next to me, sitting in front of us, is a world-renowned quantum physicist. And his topic, what he's going to speak on, of course, quantum physics, free will, and so forth. And the series of the talk, which is the Padmapani lecture, as I said earlier, symbolizing the lotus, the one holding lotus, symbolizing the Buddha of compassion. So while there's a tremendous, rigorous intellectual discussion happening from quantum physics, also we are not to deviate this from the heart. So today, with the presence of Professor Nicolas here, we are going to see the marriage between the two things, intellectual rigor and the heart, beautiful heart. So in the course of my initial meeting with Professor Nicolas, I came to realize that not only a great quantum physicist, but there's a tremendous heart there. You started to talk about compassion. The moment I picked up the concept of the universal ethics as proposed by His Holiness the Dalai Lama as a legacy, as a gift for the world, he instantly picked up the thought, and he was just moved by this talk on compassion. So here is a person who really symbolizes the harmony of the great intellectual rigor of quantum physics and the beautiful heart. So without much ado, I'd like to request our moderator to introduce to you, to make a quick intro of the speaker today, Professor Nicolas.
Thank you so much. Thank you so much, Professor Nicolas Gisin was born in Geneva, Switzerland in 1952. His interests cover a wide range of topics from the foundations of quantum physics and philosophy to applications in quantum communications. He was awarded many large projects and prizes, authored hundreds of scientific papers and a popular book on quantum chance and non-locality, and is a co-founder of a successful company in quantum cryptography. The topic he'll be speaking on today is quantum non-locality, randomness, and free will. Professor, you may take the stage.
Well, so thank you very much for these very nice introductions. So, being a physicist, I think I'm going to stand up. Can you hear me? Everybody, no? So if I speak loud enough.
No, for recording.
So maybe I go down. I don't like so much to step up.
Doctor, for recording purpose. For the recording purpose.
You want me to have a microphone?
Yeah.
Is that a microphone? Decoration.
No, this is for the recording. No. Just 1 minute. So he's blinking. No. Sharon, no, Sharon. No, they're blinking. Give us 1 second. Dr. Nicolas, he's blinking.
Yeah.
He's blinking
Just
one.
wait, it's fine.
Yep.
I feel more at ease if I can speak with my hands. I'm not Italian, but still.
Very close to Italy.
Very close indeed. But there's still one chair here. Very close. Chair.
Who's the publisher of your book?
Excuse me?
Who's the publisher of your book?
Odile Jacob. So Odile Jacob for the French version, and the English version is by Springer.
Springer.
Is it on? It's on? Can you hear me now?
You don't switch it on.
Yeah, it is on.
Probably need to bring it closer to you.
Like that?
Yeah.
Okay. Good. Okay, well, thank you everyone for being here. As you see, I have slightly changed the title, but it has the same meaning. Physics, quantum physics, I think I said, is the future. You will see it's connected really to the original title here. What you see here is a beautiful clock I have in my office in Geneva. And what is a clock? It's a beautiful mechanical object which is made on purpose for being extremely predictable. Now you want to be able to predict that in 12 hours the clock will be exactly back at its initial position. That's the purpose of a clock. And this is indeed a very good clock, so it is easy to predict. So it is deterministic. there is on the other side an example which is more a quantum example. I don't know how many physicists are in the audience, but you know that you have atoms, and atoms can be in their ground state or can be in an excited state. And if then they are in something that we call a superposition, they evolve also in an extremely predictable way, as shown here. And this is actually the basis for atomic clocks. And atomic clocks are the most predictable things in the universe, at least man-made, in the sense that really after even 1 million years, essentially the clock will still be on time, be up to a second or a fraction of a second. So these are two examples of typically deterministic evolution. Very easy to forecast. We know exactly what's going to happen. And actually, when I was young, 40 or 45 years ago, I was really thinking our nature is really beautiful. Nature can be understood. And nature is really a kind of super complex watch or clock. Something like that, with many cogwheels that push each other, or many little balls that, why did that disappear now? The computer is a bit slow. Okay, now it's moving. So you see all these little beard balls, kind of little atoms that push each other. This is Brownian motion. And again, so it is very complex, but there is nothing unpredictable. If you know everything, in principle you can compute everything. And I find that is really fascinating. However, today I realize that this mechanistic worldview is a kind of a nightmare. It's a nightmare because everything would just be the unavoidable unfolding of some initial condition and natural laws. So everything just happens by necessity. There is no room for anything except necessity. And so everything would just be the consequence of some, let's say, quantum fluctuation at the time of the Big Bang, when everything started according to today's physics. And so there would be no future in the sense that everything would already be there. There's no way to be creative. Free will would be an illusion. Time would be an illusion. Consciousness is an illusion. Mental attitude is an illusion. Nothing really exists in this sense. Everything just follows from the initial condition. Moreover, physics is often presented as the example of a good deterministic explanation of the world. And now people say, okay, everything has to be explained like that. So all good explanations should follow the structure of physics, of this physics which is so predictable. Everything is predictable. And really, for physicists, my colleagues, scientific determinism is really an extraordinarily strong view. Everything is determined by the initial condition of the atoms and quantum that make up the world. Nothing beyond that has any independent existence. So there's no independent character, no reason, no power, no emotion, no consciousness. That is the view of physics as I learned 45 years ago. And I find that quite a nightmare, because essentially people then say, well, what is not in the equations does not exist. So for instance, the entire world would be like a movie, in a closed box. So here the box is open, but you imagine easily close the box without any spectator. There is no spectator looking at it. Spectators that may have emotions, that feel the time passing and so on. That disappears. And so I thought, okay, this is a horrible picture, and physics cannot be like that. What's going on? And actually, such a dreadful deterministic, mechanistic worldview is scientifically wrong. So this is the main message, actually, of my entire talk. I will, of course, elaborate on that. That will be the main message. But essentially, this worldview, which is purely deterministic and mechanistic is simply wrong, and it is scientifically wrong. So science really allows us to be sentient beings and actors with emotions, free will, and consciousness. Of course, that doesn't mean that science explains consciousness and so on. I don't claim that it explains. I'm just saying it leaves room open. There is room open so that it is compatible. So here is now an example of something which is kind of the typical quantum randomness, so quantum non-determinism, the opposite of determinism. And so people who are a bit familiar with quantum physics have already seen that you have a stream of photons. Photons are particles of light on a beam splitter, a half-silvered mirror. And then some photons get reflected to a detector, which you may label 0. Some get transmitted to another detector, which we label 1. And when we get a stream of 1s and 0s, and these are random, and this is really the archetype of non-deterministic evolution. And then usually if you go to textbooks, quantum physics textbooks, you will see something like that the structure, so quantum state and experimental arrangement, determines, causes, that there are only two possibilities. So the photon will never go up or go down. It will either go left or right. So it's not everything that is possible, but there is more than one possibility. So there are two possibilities, that's more than one. But at the end, you have the two detectors and only one realizes. So one detector will click. And there is some propensity for each of these two possibilities. So the propensities are determined, but the result is not determined. So this is the typical example of quantum physics. And this actually you can even make a little device. And I brought here an example. So this is an example, and this is a real one. You can put it in this kind of computer, and it will really provide you with quantum randomness. And actually this is something which my company, I will mention a bit later, is really producing and selling, so it means people are buying that. So maybe you find that an argument or not an argument, but at least it's something that the society and gaming industry, cryptographic industry is really using. So they believe in that. Very good. Maybe you can just let it go around. Please give it back to me because I need it next week in Sikkim.
Professor Gisin, if I might interject.
Sure.
This is a completely random sequence, right? It's not a pseudo-random sequence.
No, exactly.
Completely
it is
random.
a completely random.
So
absolutely. It is not pseudo or semi-random, it is truly random. So this is indeed the claim. Now, why should you believe in that claim? Because I told you, but that's not a good reason. So why should you believe in that? So why actually quantum physicists convinced that we are truly random? And in order to tell you why we are so convinced, I'm not going to do a mathematical demonstration, but to tell you a bit about the arguments. And in order to explain that, we don't need one of these devices, we need two of them actually. And we put them at some distance, and one we call A or Alice, and second is B like Bob. Just to have two of them. And also we need that these devices have some inputs, that I can change something in the device, turn this polarization beam splitter a bit, or something like that, to act on a phase. So I have some possibilities to make some change here, and of course I get the results. That's the normal thing. This thing that you have here provides results. Provides, by the way, 4 million of random bits per second. Okay, and the same here. Okay, now in order to make a real proof, to make a rigorous statement, scientific statement, I need some assumptions. And you see the assumptions are quite minimum, but I want to be very explicit with you, so very honest. So one first assumption is that we need to assume that distances really exist. So when I say I put Alice on one side and Bob on the other side, and you will see they can be 10 kilometers away, really large distance, that means really that there is a distance. And I will even emphasize that a bit more, elaborate on that. The second assumption is that there are independent inputs, these x and y, these choices here and there. They can be made and are independent of the system. So what does it mean, these two assumptions? Let's first, about the first one. Distance, it means that it takes some time to go from one location to the other location. Now, if you have 10 kilometers, well, in the daily traffic, you can imagine it takes a huge time. But even if there is no traffic and you can go at the speed of light, or maybe you can even go faster than the speed of light, if there's a real distance, it will take some time. Maybe only a fraction of a second, but it will take some time. Not zero time, some time. Now, it takes time for everything. Everything will take time. Nothing can just jump from A to B in no time. That is an assumption. I think it's a very reasonable assumption. It will take some time to go from A to B. The second assumption about this independence here can be illustrated. So for instance, you could imagine that this x, the choice here of this setting here and the choice of the setting here, is determined by the digitalization of some old movie or old recordings. Actually, that has really been done in some experiments. You take an old movie from the 60s and you digitalize it, and then you have a string of bits. And these bits you can use as an input here to make your choices, how to orient your polarization beam splitter or your face. And maybe here you take a picture of a very old hieroglyph or something like that, something very old or from some archaeological site. So now this very old archaeological site, this old movie, they are clearly independent of the experiment we're going to do. Now, if you don't believe in this independence, you cannot do science. You can no longer think. There must be something independent in order to start an argument. So I would say that these are assumptions, so I write them explicitly, but they are extremely weak assumptions. Okay, now from these two assumptions, plus a fact, it's an experimental fact that we do in the lab, you can check that you can run such an experiment and observe that a certain equation is satisfied with high probability, about 85%. Okay, maybe you don't want equations or you don't understand equations too well. Okay, for those who understand, this is addition modulo 2, so add two bits, and this is a product. You know what a product is. You have two numbers. These numbers, by the way, are 0 and 1, so very simple numbers, and you multiply them. Very easy, to multiply two numbers. And that succeeds with this high probability. So this is already a bit strange if you think about it. Because this multiplication is, of course, very easy to do. We'll do it together in a moment. But the difficulty is, how can nature compute this product when x exists at Alice's side, let's say very far in that direction, and y exists 10 kilometers that direction? So they don't know each other. No? They are kilometers away. How can we know the product? Now, Alice knows x, but doesn't know y, so doesn't know the product. Bob knows y, but doesn't know x, so cannot know the product. So it sounds still a bit strange. We elaborate on that. But already you have the intuition, here is something interesting going on. So let's just look at this little equation. So if both are equal to 0, then of course 0 times 0 is equal to 0. And so saying that a plus b equals 0, if it is an addition modulo 2, that means it can be 0 plus 0 equals 0. It could be 1 plus 1. 1 plus 1 is equal to 2, but when we compute modulo 2, it's also equal to 0. If you're a bit lost with the equation, just wait for the next slide. It will become easy again. Here, if it's 0 times 1, 0 times 1 is again 0. 1 times 0 is again 0, so it's always a equal b. However, if x and y are both equal to 1, then 1 times 1 is equal to 1. He's smiling, so I know that he knows. And 1 means, well, could be 0 plus 1 is equal to 1, or 1 plus 0. That means A is different from B. Okay. So intuitively, you see, how could you do this multiplication? Well, intuitively, you say, most of the time it's equal. So maybe 3 times out of 4 it is equal. So the probability of getting that equation satisfied could be 3/4 easily. And this is actually technically something called a Bell inequality. And remember, 3/4, that's 75%. 75% is below this 85%. So we are better than that with quantum physics. So there's still something strange going on, something worth analyzing. That's exactly it. Okay, and now, so there's a correlation here. You get this surprising high correlation. So when you get a correlation in science, whether it is in medicine, or, you look correlations between some medicine and the health. If you get better, then it's a positive correlation. Or in geology, I don't know, you look at some science and you look for earthquakes. I mean, in science, you always look for correlations. And then once we found some correlation, we want to explain that, find an explanation. Now, in classical physics, there are not so many sorts of explanations. Again, everything, mass, energy, information, propagates gradually and continuously through space as time passes. Nothing jumps instantaneously. And that means you have only 2 possible explanations for correlations. Either you have a common cause in the past. So for instance, now the guy is there and there. You get correlated. You get correlated by me emitting sound waves that go both this way, that way, also to everyone, hopefully. And then it takes some time, of course. It goes pretty fast, the speed of sound. But you get correlated in the future by my sound going to each of you. So this is this kind of explanation. There is a common cause that propagates from some origin. So myself, in this example, goes to one guy, to another person, actually to everyone here, and you all get correlated. You all hear the same. That is the first kind of explanation of some correlation. There is a second explanation of correlations, which is also very easy. I speak, my wife hears it, we get correlated. Again, there is something going from me, sound wave again in this example, from me to her, we get correlated. This is really a direct cause. So we can have a direct cause from me to any of you, and so we get all correlated, or between you guys via my producing a common cause for each of you. Okay? And if you think a bit, correlations are always explained like that. At least in classical physics, it's always like that. So let's look. We have now these correlations between these 2 quantum random number generator. Can we explain them? First, okay, so just to show you some examples. So this is Geneva, the Lake of Geneva, the Swiss Alps. By the way, today it is snowing in Geneva, so it's much colder than here. And so we did some experiments already 20 years ago. So we had Alice a bit north of Geneva, Bob a bit south of Geneva. We were using optical fibers from the Swiss national telecom operator. And here you have some, just that you remember that this is a real experiment. It's not a thought experiment. This is really real. And we could indeed show that in this experiment with these 10 kilometers, a bit more than 10 kilometers, we had the probability of this equation being satisfied larger than 3/4. So technically we say we violate the Bell inequality. It's larger than 3/4. This is another more recent example, 2-3 years ago in Delft, where we did also some experiments. Okay, the distance was a bit shorter, but they had, kind of nano diamonds. And so they had also these kind of correlations, not with photons, but with massive objects. Okay, very nice. So we see that these correlations exist according to the theory, but also exists according to experiments. So it really exists in nature. We can really make them. So we need to explain them. So the idea first would say, okay, maybe there's a direct cause. Maybe, let's say this is Alice on one side, and Alice not talks, but influence something very, very quick to Bob. Or maybe it's Bob on Alice, doesn't matter. But there's a direct communication, like me to my wife now. How can we test that? Well, to test it, the idea would be that we're going to make an experiment here, and really at the same time do an experiment here. So we're going to ask the question, is X and Y. We put them at the same time in, and very quickly collect the results. How to do that very, very fast. And if we do that very, very fast, there will be no time for this influence to go from A to B or from B to A. Very simple, no? If you ask, okay, now my wife is too close, but if you send them to Geneva and I talk over the phone, it takes some time for her to hear what I say. So if you ask her an answer, a question, before the time of the communication, she cannot know, because it takes some time, because there's a distance. So we did that kind of experiment. Okay, it has been reproduced by other guys then. And okay, I don't know how many people here know about relativity, but you need to take into account relativity, because when I say at the same time, it depends on the reference frame. So maybe I'm not going to explain that, but if there are some physicists, you're welcome to come to me afterwards and I can tell you how you do that in all reference frames. Here I'm just going fast, so you use the fact that the Earth is rotating, and you get that if there would be a direct cause, this influence would have to propagate, according to these experiments, at least 50,000 times the speed of light. So you all heard that nothing goes faster than the speed of light. No? Now here we even tell you it cannot, for a direct cause explanation, it would even have to go 50,000 times the speed of light. So physicists would tell you this is impossible. Actually, some of the latest experiments, the last one here, I think even went to about 500,000 times the speed of light, something like that. I don't remember the exact number. But very, very, very fast. And then we even have some theoretical argument, which I'm also not going to explain, but if there are some physicists, you are welcome to come to me or ask questions afterwards, where we really just from a theorem, so it's pure theory, but having not two parties, not only Alice and Bob, so Alice, Bob, Charlie, and Dave, and a more complicated and elaborated argument, we can really prove that these non-local correlations based on finite speed causal influences cannot exist, because they would lead to superluminal communication, which contradicts relativity. So the conclusion from no, there's one more here. That's very nice also, at least for the physicists. Are there any physicists here? 1, 2, 3. Okay, good. Oh yeah. Okay, so it's good to. Okay, very good. So here is an experiment which I find very nice. Okay, maybe lack of modesty. Again, you take Alice and Bob, and you have them move away from each other, very fast, hundreds of kilometers per second, per hour. Sorry, depends on. Okay. And then you can do that in such a way that Alice, in her own inertial reference frame, does the measurement before Bob. But Bob, in his inertial reference frame, does the measurement before Alice. So each one is doing the measurement before the other. So of course they cannot get influenced by the other, because I'm doing it first. How can I be influenced by you? You are doing it first. How can you be influenced by me? So that is really also a very clear, neat way of making sure that they cannot influence each other. There cannot be any direct cause. Okay? So you see there are lots of explanation of experiments and also these theoretical results. And the main conclusion from all that is that the observed quantum correlations cannot be explained by direct cause. So this explanation is eliminated, cannot be. Okay? It's a very, very precise arguments. So maybe it is common local cause. So let's look at that. So the idea, okay, there is no communication. We have said that no direct communication. Still there is this product here. How can we do the product, compute the product? X is only known to Alice, and Y is only known to Bob. So the only possibility, and this can be proven more seriously, but it's quite intuitive, what you can do is to bet that X times Y is equal to 0, because this happens 3 times out of 4. So it's the most likely. One that this happens only in 1/4 of the cases. So you bet on 0, and then that happens 3 times out of 4. So you get this Bell inequality, which I have already introduced once. But this can really be made very precise also, more mathematically. Okay, and now you do the experiment. Already showed you. The experiment shows 85%. 85 is larger than 75, which is 3/4, no? Conclusion? Well, you cannot explain this observed quantum correlation by common cause. So this is eliminated, and now this is also eliminated. What is going on? We have eliminated the 2 possible explanations. But these quantum correlations exist. We have observed it. Many people around the globe have observed them. Oops. Yeah. So somehow nature can coordinate at a distance without communication and without prearranged output, without this common cause. So physicists say, okay, nature is non-local, able to produce non-local correlations. And maybe, there's nothing more here. It's coming later probably. So once you have that, then there's a theorem. It's really a mathematical theorem. Nothing to discuss. You have the assumptions. Distance exists. Nothing jumps from here to there instantaneously. You have these independent inputs. And you get, that you can have probabilities of this equation being satisfied larger than 3/4. And then the theorem tells you that the necessary consequence of this is that the outcomes, A and B, what comes out here of these devices, the outcomes result from intrinsic random process. So now this is really why the physicists are so convinced that this thing, which is somewhere now in your hands, is really producing intrinsic true randomness. It is not like a clock. It is not like an atomic clock or a mechanical clock. It is not just cogwheels turning or billiard balls bouncing into each other. There's something intrinsically new, hence interesting. And you can make it a bit more precise. So at 85%, each time you get a click, you have, according to these assumptions, you have about 0.3 bits of randomness, or the entropy is 0.3 bits per outcome. Or if you believe in quantum physics, then it would even be one random bit each time. So depending on the assumption. If you make one more assumption, namely quantum physics is correct, then you get full randomness. With the assumptions I have written here, you get 0.3 random bits per event. So how can we explain that? How can we talk about that? We need some new terminology, because we can no longer just think of these cogwheels pushing each other, these billiard balls pushing each other. So I'm trying to here propose or suggest some way of talking about these non-local correlations. So one way is to say that quantum correlations imply non-local randomness. One random event can manifest itself at several locations. So what is happening here on Alice's side And what is happening here on Bob's side, they're at a large distance, 10 kilometers in this example. But it's the same event, the same random event that appears there, with these huge correlations. Very surprising. So if you find this is obvious, you didn't listen carefully. It's very surprising. But it is a fact. Or maybe you can also use this kind of terminology. Quantum correlations somehow emerge from outside space-time in the sense that no story within space-time can explain how they obtain. If I want to tell a story within space-time, I can say, yes, something goes from here to there, or from here, both to here and there. I have to explain something like that. That's a story in space-time. That's the usual story we tell. But that doesn't work here. This kind of story doesn't work here. So you may say, okay, there is somehow, in some sense, these correlations happen from outside space-time. By the way, these are kind of terminologies I have used in papers published in big journals, Nature, Physical Review Letters, and so on. So it's not something I have just invented for this talk. So this is something completely new. It's really a revolution. Okay, it's not from today, this revolution, but quantum physics and all this stuff really started 20, 30 years ago, something like that, pretty recent. And when you have something really new in science, it must have some applications, some consequences. You don't have something completely new, and you cannot do anything new with it. Here is an example of something. Let's put Alice here, with a choice between 0 and 1, so this is this x 0, 1, same for Bob here. And initially, okay, you let these Alice and Bob share some quantum stuff, some photons or something, some atoms, doesn't matter. Okay, when you close them, you have Alice on her side, Bob on his side. Then they choose these x and y, and they get results, A and B. Exactly as I showed you before. But what is now interesting is that you do that very often, and then by public discussion you can estimate what is the probability of getting A and B given that Alice and Bob have chosen X and Y. You estimate this probability by some statistics, and then the fact is that if this probability here violates some Bell inequality, essentially this equation I showed you before is satisfied with a probability larger than 3/4, then this correlation contains secrecy. Somehow, non-local quantum correlations are cryptographic keys. So you have something secret going on. And this you can understand intuitively. You have this non-local randomness. So only Alice and Bob will get a copy, but they will get copies highly correlated. And what do you want when you have a password? You use old passwords. We all use passwords all the time. We forget about them and so on. But we have a password. What is a password or a cryptographic key? It is a random sequence shared between, let's say, your bank and yourself, or Amazon and yourself, it doesn't matter. But it must be random and the same on both sides, highly correlated. So intuitively you see that this non-local quantum correlations, or this non-local randomness, is precisely a cryptographic key, something very useful in today's society. We would like to have automatic passwords. Okay, for ourselves, not very important, but maybe for banks or governments, or I think also hospitals that deal with a lot of health information about our health or the health of our children. We would like that to remain confidential. And this is a way of doing it. And so indeed, we could, with this company, IDQ, the same as the one with this random number generator, developed quantum cryptographic boxes. And you can buy them if you like. So now this is Alice, this is Bob. Okay, once it has been industrialized. They don't look like Alice and Bob, but that's just a electro-optic instrument And with these instruments, you can, for instance, have one in Geneva, my hometown, one in Lausanne, okay, that's about 70 kilometers away, and you have an optical fiber below Lake Geneva here. You recognize I got the random number generator. And in this way, you can now establish cryptographic keys between Geneva and Lausanne. This is an application. And so my company I contributed to, so it's based in Geneva. We have offices in Boston, in Hangzhou, in China, in Bristol, and this year we are opening new offices in Korea, in Singapore. Okay, we are 60 people in Geneva, altogether maybe 100 people. So I'm just telling that it's real, in the sense that it reaches the outside world, the commercial, industrial world. And I find it also very nice to have this kind of balance between the very conceptual, philosophical side, connected to Buddhist philosophy, but also the industrial, very down-to-earth side. And I think if you do something really new, original, it's good to have the two and have a good balance between these two opposite sides.
Is this a good time to ask a question, Professor?
Yes, very good time indeed.
Thank you. So what does this product do?
So
whoever buys it,
Okay.
what does it do?
Yeah, good question. So there are two products. No? There is the one that is circulating that just produce randomness, random bits. And so people producing cryptographic equipment, we need that. It's a way of producing passwords, also for the gaming industry, or also when you do Monte Carlo simulation. You need randomness. So you need a lot of randomness, and this is just a true source of randomness. The second one, these two boxes, Alice and Bob, this is not localized randomness, but non-local randomness. So now you can have one for you and one for a friend of you, or it's a bank and another bank, or hospital and another hospital, and so on. And then they can automatically produce passwords or cryptographic keys that exist now in the first hospital and in the second hospital. And we produce fresh cryptographic keys, let's say, every second. So we continuously change the cryptographic key.
So you can scramble information at one end, scramble it from one end and receive it good at the other end.
Yes, exactly. But at the other end, you can unscramble it.
Yes, sure.
So indeed, in between it is scrambled. So if someone tries to intercept it,
Sure.
he will just get a scrambled message.
Sure.
But you can do that. So you can do that also with all kinds of randomness. But here the advantage is that first it's true randomness, it's not pseudo randomness. And secondly, because now it is automatic, you can change this key every second. You know, normally you would have to send someone from one place to the other, and that would take time and so on.
Professor, if I understand correctly, since this is non-local randomness, you don't need a communication channel between the two parties to transmit the keys?
No, you don't need any communication to transmit the keys, but you need a communication. You still need an optical fiber to distribute the entanglement. I didn't use the word entanglement, but you know.
But your key is secure.
Yeah, your key is secure.
Which you need as a cryptographic system.
Exactly,
Right.
exactly. But you need to distribute this resource, this non-local resource, which is entanglement. That's the technical
So
word.
you send paired photons to both,
Exactly.
and then they will generate their keys at their stations.
Exactly, exactly. Very good.
Did you have it software based totally, or
No.
you need the hardware?
No, you need the hardware here. With pure software would be classical. Of course, software is usually done with conducting devices. But in principle, you could all do that with billiard balls. Simply, it would be very slow if you do it with billiard balls. But everything you can do with billiard balls is classical physics. And this is really quantum.
Sir,
it's back here. Very good.
sir, is there any relation between quantum entanglement and this?
Yes. So I didn't want to use the word entanglement, but entanglement is the resource to produce non-local correlations, or quantum correlations. If you want, entanglement is the technical scientific word to say non-local quantum correlation.
Let's make sure that there's a flow in the talk, and then in the end there's going to be question answers. Please reserve the questions then.
Okay.
Okay, so now we have that. The light is back, so we can continue. Okay, so now what does all that what I've said so far imply? So does it imply the end of determinism and the end of this mechanistic worldview? And for sure, yes, that's the end of mechanistic worldview. So there are no cogwheels. You know, when you have 10 kilometers in between, there's not a cogwheel pushing each other. There are not little billiard balls pushing each other. It's really the end of this mechanistic worldview of classical physics. Now, what about the determinism? So here, probably some of you, the physicists, will have heard of Bohm. By the way, was a friend of His Holiness the Dalai Lama. And there indeed there's something called Bohmian mechanics. We just mentioned it for those who know. But Bohmian mechanics rejects the assumption that distances are real. In the sense that according to this theory, when you do something here, it has an immediate influence everywhere in the universe, instantaneously everywhere in the universe. But if you buy, as I do, that distances exist, when you reject Bohmian mechanics, and by the way, Bohm himself rejected what is today called Bohmian mechanics. There is also another alternative view on quantum physics that maybe some of you have heard, namely this many worlds. And this is again deterministic. So many worlds rejects the assumption that when we do an experiment, one and only one result produces. Many worlds says that if I do an experiment with two possible outcomes, both happen in parallel universes. My sentence is grammatically correct, but I have no understanding of what it means. This idea, I'm interested in the world in which I live. A parallel universe with which I have no contact. What does that mean? So okay, I reject that. I guess it's a good illustration of how difficult it is for everything that happens, for instance, in my brain. Quantum mechanics is not important. Quantum mechanics in the brain is irrelevant. I'm not sure about that, by the way, because even very small effects can be amplified. But they say, now for these kind of things, you have to go back to classical mechanics, and classical mechanics is deterministic. So the brain is deterministic, so we get back to the idea, no consciousness, no free will, no mental attitudes, whatever. So we get back to my clock. So how does that go now here? Indeed, we learn that classical mechanics is deterministic. We have Newton's equations, Maxwell equations, which are indeed deterministic. So in the sense that given some initial condition, the future and the past are in principle determined. But does that really mean now that nature, or let's say described by classical physics, is deterministic? Let's here to take an example of something which is not like a clock. This is something much more typical. It is a typical classical dynamical system. Like, for instance, the weather. The weather evolves, but it evolves in a much more complicated way than a clock, and much less predictable. Just look at the weather forecast. I don't know how it is in India, but in Geneva it is not predictable. And let's suppose we have some range here between 0 and 1. Let's say 0 means it's highly likely to be rainy, and here it is highly likely to be sunny. Now you can make a change, a dynamical change here. You stretch that, and then you fold it back. So mathematically, you have some equations. Now if you write this position here between 0 and 1 in binary form, so 0 point, and then you have all this. So in this case, it's not digits, but bits, similar. this transformation here is just like that. The first bit you forget. The second one, now you shift to the left. It becomes the first one. The third one becomes the second one, and so on. You just shift it. It's a very simple transformation. And this really can exist as a classical dynamical system. Now, whether x lies on the left or the right part, on this part or on that part, after n time steps, depends on the nth bit of the initial condition. So each time it goes one step. So of course after n time, the first bit is the nth one. Okay? Now here it is sunny on the left, rainy on the right, the opposite of what I said. Now let's say after 1,000,000 time steps, it should be the millionth bit of the initial condition that determines whether it is sunny or rainy. But does that millionth bit have any ontological reality? Does it make any sense? For sure we cannot measure it. Technologically impossible. But even, does it really exist? Do we have to give it any ontological and physical existence? You can say yes, you can say no. But important, you have a choice. You can say no, it doesn't exist. No one will be able to falsify that, to contradict you. And that means that somehow these real numbers that go on forever, they are anyway uncomputable. There is no computer that can compute a typical real number, because you only have finitely many or computably many programs that you can run on a computer, like this computer. And so you can only computely many, so 1, 2, 3, 4, that you can count, while the number of real numbers is a continuous infinity. So most of the real numbers, there is no way to compute them. That means that most of the real numbers are actually random, in the sense that the sequence of digits are truly random. And they're truly as random as what comes out of a quantum experiment. So you can really think that the digits of a typical real number are as random as what comes out of this quantum random number generator. This is really something that Grégoire Chatin, a mathematician, has elaborated at length, and you may like to read more about it. So I don't want to go too much here. But you see that in classical physics, if you want to claim that it is deterministic, you have to claim that real numbers are really real. You give them ontological, physical reality. But if you don't do that assumption, then classical physics, like quantum physics, is non-deterministic. So that's what I'm writing here. So clearly I'm on the side of saying that mathematical real numbers are physical random numbers. Actually, I just put a paper on the archive, if you like. But if you would not call these numbers real, so this from historical reason, Descartes, a French philosopher, called them real, okay, for historical reasons, but maybe a better name for these numbers is a random number, because after all, the digits are random. And if you would call them random, you would never have used random numbers as the basis for classical determinism. So the argument here is that classical physics is also indeterministic. Okay, let's go faster here. Okay, so now we have seen that, and this was a very, very strict argument, that quantum physics is non-deterministic. It's not mechanistic and it's not deterministic. Classical physics is mechanistic, but whether it is deterministic or not is your choice. Depends how you consider real numbers, and you can really decide. It's not necessarily deterministic. So we have opened the future somehow. We have opened the possibility that there is some flexibility in this physics worldview.
Does that now explain, I don't know, consciousness or free will, this kind of stuff? No. I don't think it explains it. It just leaves room for it, which is good enough already. You should not confuse some form of philosophy and physics. However, my position, so now I'm just telling you my epistemological position, is that if you want free will in the logical order comes first. Because if I had no free will, if you have no free will, how could you decide that what I'm saying is interesting? Or maybe you're going to buy my argument. Or how could you decide that what I'm saying is not interesting and you don't want to buy my argument? Just in order for us to enter in some argumentation, some discussion, each of us need to have some free will just to decide, yes, I buy this argument, no, I don't buy that argument. Without free will, you cannot even start a discussion. This is how I see that. So free will is actually a prerequisite to do philosophy, but also to do science. And consequently, neither philosophy nor science can ever disprove the existence of free will, because you need free will before you start philosophy and science. And so there's this French philosopher, not a very well-known, who said that without free will, the certainty of scientific truth would become illusory. And I added, consistency of rational arguments would equally become illusory. So this is how I see it, and maybe my almost last slide here. So now we said, okay, physics is indeterministic. So there exist, of course, things outside. I mean, I'm still a physicist and probably not really understanding Buddhistic vacuum or no, emptiness, you say, emptiness. This I don't understand yet, I have to admit. So things exist, they're out, that's the usual old Descartes view. But what I add to that is res potentia. So there are also potentialities out there, possibilities out there. And so we the physicists are not used to this idea of potentialities. But clearly in our life we live with full of possibilities, dispositions, propensities. By propensity I really mean a kind of indeterministic force. There is more than one possible future. For the photon to go here or there, or also for myself to go later tonight this way or that way. And so one of the beauty here of this res potentia, the possibilities, it's not that everything is open. I can decide to go left or right, but I cannot decide to fly. So not everything is possible. Like for this photon, it can go one way or the other, but not everything is possible. So some things are possible, but most of the things are impossible. But structure still leaves me a little bit of room. And this applies to individual cases. I don't always need to make statistics, but of course if I run that and accumulate many similar individual cases, I will get frequencies out of that. Okay. Okay, so I come to my conclusion. So the main conclusion and the main message, the one that you should really remember, is that according to quantum physics, nature is non-deterministic. And actually, if you admit the idea that mathematical real numbers are physical random numbers, then even classical physics is also non-deterministic. Except for the rare cases where you make a clock or harmonic oscillators. If you make something very made for the purpose of being predictable, can be predictable. But if you do something which is more frequent, like a weather forecast or most of these things, it is non-predictable. Okay, so the future is open. This is my book in which I don't say too much about classical mechanics and about free will, but I say a lot about the quantum randomness, quantum chances, the title says here. So thank you very much for your attention, and I'm waiting for your questions.
Okay, the questions, I really like to invite questions, no lectures. Okay, to the point, just one question per person. Over there.
Could you, sir, please explain the difference between quantum chaos and classical chaos?
So classical chaos is okay. The example I gave of this classical Baker transformation, where you shift the bits to the left. This is a typical example of classical chaos, where the future is hypersensitive to the initial condition. And so if you don't think that the initial condition is defined with or exists with infinite precision, then you get this classical randomness. Now in quantum, it is very different in the sense that you don't have quantum chaos in the sense of sensitivity to initial conditions. What you have is, first of all, you have sensitivity to the boundary conditions, like the Hamiltonian, for instance, that would be sensitive to that. And you have that the result of these measurements are random because, under the assumption of locality and independence. So you get randomness in quantum, but it's quite different from the classical one. We can discuss more, I think. It's very interesting, but difficult to say more here.
Okay, Mr. Carnegie.
Yeah.
Sir, I want to ask you, how do you say that indeterminism cannot explain free will? Is it not that indeterminism is extreme determinism and it explains the free will phenomenon?
Can you repeat the last part?
You say that indeterminism cannot explain free will.
Yes.
But is it that so-called indeterminism is absolute determinism, which is beyond our comprehension today?
Yeah,
that is why free will is there.
Yeah, maybe, but I think, I don't want to contradict you, but I think you're making some more steps that go beyond standard physics, no? Standard physics can only say that the world is open, there is indeterminism. But just indeterminism by itself doesn't explain free will. Now, in free will, I don't want to just make random decisions. Random decisions would not be free will. I want to have some control over my decisions. So you need something more. And I think this indeterminism leaves room for this possibility, but I don't think it explains it. So maybe you can add something with what you say, this extreme indeterminism, which I'm not sure I fully understand, that this could possibly then explain free will. But I think this is an additional step that you are doing.
Excuse me. Yes. When you say that we have free will, it means that we are free to decide.
To decide?
Or is it that the strongest motive is decided by necessity?
No, it's the first one. So we have some possibility of making choices, so we can choose among several possible futures. But not all possible, not all futures. I cannot decide to start flying. So, but there is a certain number of possibilities. Importantly, there is more than one, and then I can choose among them. And there could be propensity. So maybe this one has 3/4 propensity, this one only 1/4. So I may be more tempted to go that direction for that direction. But depending on the day, depending on my decision, my free will, I will choose this one or that one.
But if you said depending on the day and depending on external circumstances, then it is
depending on my free will.
But it's conditional then, it's not absolute.
But the free will you call free will is conditioned by a set of possibilities which you can't compute. So that's why you're calling it free will.
And the strongest motive decides for us.
I don't think it's always the most likely which is going to happen. Maybe sometime I will use my free will to...
The motive which is strongest in our mind. That is what decides. It could be different on different days depending on the circumstances or whatever. This is what all philosophers are generally on free will.
I think perhaps the question can be summarized like this. Say, if I choose to, raise my hand like this, right? And then you will say you use your free will. I use this free will of raising my hand. So then if you ask me, okay, you use your free will, yes. why did you raise your hand like this and not like this, right? Because I feel more comfortable this way. So you always give a reason. When you give a reason, which means that it is determined some other factors. So how can you still call that as free will?
Because at some point, if you do this analysis, this chain of causation
exactly
opens more than one possibility. And at some point, you could indeed say this one or that one. I don't know. There are several possibilities that were all possible, and you have really to make a decision among these several possibilities, and in this sense it's your free will. So there is a causation, but this causation causes that there is a finite and a structured, limited number of possibilities, but still more than one.
Okay, so any more questions?
Great
One over there.
demonstration
Sorry. One over there.
Thank you, Professor. This is most wonderful. I do accept what you said about free will. Absolutely perfect. But a question. As we experience the world, there is a macro world, then there is a micro world, and of course, the less familiar nano world. And if I may say so, what you said about quantum physics and all that applies more to the nano world than to the macro world. And in the macro world, we find determinism, by and large. I mean, if two cars sort of run into each other, we know what will happen. There is no indeterminacy there. Thank you.
Okay, so I understand the question. I think so. This object which I let circulate, which is probably somewhere now, here it is. This is not microscopic. You can see it with your naked eyes. No? This is producing randomness, so it comes from quantum physics. But at the end, what comes out is an electronic signal which is clearly microscopic. You can turn on and off lights with that you can just see. So this quantum randomness can really be brought up to our scale. No doubt that you can bring that up to our scale. We do it all the time. And for the second part of your question, namely that you say, okay, if two cars bump into each other, it's going to be an accident and so on. That I fully agree, of course. But it is not because in classical physics there are some examples of determinism, like the clock, that was my example. Your example is cars that bump into each other. That is deterministic. But that doesn't mean that all the classical physics phenomena are deterministic. For instance, again, the weather is also kind of classical phenomenon. It's sunny or rainy, and this is not deterministic, or at least it is chaotic. And if it is chaotic, it would depend on the very, very far digit of the initial condition. And if you say that these far away digits of the initial condition don't have physical reality, then classical physics again becomes indeterministic, at least in certain circumstances. And actually the cases in which classical physics is indeterministic are much more frequent than the cases in which it is deterministic. It's the case of integrable systems versus non-integrable systems.
Over there, the lead over there. Yes.
I'm a lay person, so I'll ask a non-technical question.
Absolutely fine.
So I think you did this famous experiment in 1997. You're the leader of that thing that split the photons, and one went here and there, and that quantum entanglement. So one's connected, always connected. And so these things are also a part of these latest, scientific studies that there is an energy field that is connecting everything, an intelligent energy field sort of, which the 90% of the space that we see is free. Like it's space, it's not space, like we're all sort of connected through, it's not empty, space is not empty. So, and I'm asking this question because everything's so connected, like compassion and this and that. So I just want to know that if the 90% of the space that we say is empty, because this whole universe and matter is just 10% or something and 90% is empty, then, and if that empty space is actually that intelligent field, so is that also, can that lead us to understand what is this dark matter and dark energy in the future?
I don't know. I don't know. You know, this dark energy, dark matter is unknown today. What you said is intelligent field is also, from the physics point of view, unknown or not understood. And it's not because you have two things that you don't understand that you put together that they are going to resolve each other. So the answer, the honest answer, is that physics has no answer to your question today.
Yeah, this is like a very thing that people are still trying to figure out.
Exactly, but so that's part of research. So I'm a physicist, I'm a researcher, so I love questions, open questions. Your question is an open question, but I'm afraid I have no answer yet.
If I may interject.
Okay, so here, one here. Here, sorry, please.
So, what would your take be on the origin of free will?
Mic. Press it from the base. Yes, the base and the base. Yes.
So, what would your take be on the origin of free will in our human nature? While the physicists are actually trying to find the theory of everything, so if they succeed to find the theory of everything, that would explain everything in the whole world, right? So what would the origin of free will be for us?
Yeah, so you're absolutely correct that many of my colleagues are looking or are claiming that they are looking for the theory of everything. You know, people at the CERN in Geneva. And I just think they're completely mistaken and they are overselling science, and this is nonsense. So I don't think it makes any sense, the idea of explaining everything. You know, everything in an equation, and then what is not in the equation doesn't exist. So these people will claim, no, consciousness doesn't exist, time doesn't exist, free will doesn't exist, mental attitude doesn't exist, and so on.
No, but they don't claim to explain all this.
The theory of everything is supposed to explain everything. So I think this is just nonsense. And the way I would say that, you know, even if you have these kind of equations and you study them, at the end, how could you even consider that this equation or this theory is an interesting and maybe correct, or at least partially correct theory, if you cannot decide that you are convinced by this kind of argument? So it is not just a matter of pure logic. You know that even in mathematics, you have the basic axioms, the Zermelo-Fraenkel axioms. And with that, you can do a lot of arithmetic and mathematics. And at some point, you have, for instance, to decide, am I going to accept the axiom of choice? You accept it or not. It's not a matter of logic, because you can accept it and you have a consistent mathematical theory. You can accept its negation, and you also have a consistent mathematical theory. So here it's an example where you have to make a decision. You go one way or the other. By the way, you can say tomorrow I believe that, the next day I believe that. You're free to change your mind. But there is nothing, it's not a rational decision. It's not that one is good and the other one is bad. It is open. And this is even in mathematics. So in physics it will be even more open. So you need free will to make your decisions. Okay, today I work under this assumption, I believe that one, and so on. And so the free will comes first and will not be explained by science. It doesn't make any sense to think that this is going to be explained by science.
One over there, yes.
My question is a little on the fringe of science and spirituality, if you will,
Sure.
Professor.
Yeah, I'll try.
And increasingly we think that what was dogmatic is now being proven by data. So with this context, in this context, are there some quantum centers which are looking into spirituality as a thing to understand?
Well, I don't know exactly. So you're certainly correct that some of the dogmas and so on
are now proven. For instance, indeterminism is now proven on the quantum level very clearly. Now, I would also be a bit careful. You know, spirituality is very important. I mean, I'm sure to many of us here. But you cannot reduce it to science. You can certainly look at maybe the way science can illuminate spirituality and vice versa. But to reduce one to the other, you know, whether you reduce now science to spirituality or spirituality to science, I don't think you can reduce one to the other. They can illuminate each other, but they don't reduce to each other, in my opinion.
So are there quantum centers?
In Zurich there is one that is actually called Center for Quantum Philosophy, I think it's called. So you have one in Zurich. But you know, it's not because you have a center that calls itself quantum philosophy. That's just a name. Then you have to look what is there, what are they really doing.
Okay, thank you. Maybe the two last questions, one here and one there.
So
one here
is
yes.
first?
Yeah.
I was reading a book by an author called James Blake. He writes on chaos. So basically what he says is everything which is non-deterministic, like weather forecast, but there is something which is very deterministic behind it. So when you say nature is non-deterministic, you mean to say we haven't yet found out the equations which would make it deterministic?
Well, so first, on the quantum side, I mean, if you accept my two assumptions, distance exists, independence exists, the conclusion is quantum physics is non-deterministic. That's clear. Now, on the classical side, you have a choice. You have a choice, either you buy real numbers, and you say a real number is really real, you give it physical ontological reality, and then I agree that classical physics is deterministic. But it's just a choice, it's your choice, using your free will. You could also say, no, I don't think that real numbers, mathematical real numbers, are physically real. It's just a tool, it's a mathematical tool. A very useful tool, of course, but it's just a tool, it doesn't really exist. You can't say that, and you will be perfectly consistent saying that. And in this case, under this assumption that you may buy with your free will, you conclude that classical physics is also indeterministic.
But in that case, we cannot predict anything. If we go as per this concept that nature is non-deterministic,
no,
you
cannot predict the future of chaotic systems. But you can still predict the future of what we call integrable, so the non-chaotic systems. So for instance, I can still predict that my clock in my office will make one full circle in 12 hours, and even 2 circles in 24 hours, and so on. This I can still predict. So for the simple mechanical systems, I can still predict. For the cars that bump into each other, I can still predict that this is going to be bad. That's easy. But for the most general classical dynamical systems, like the weather and many more, this becomes intrinsically indeterministic.
That's what science is moving towards. That's my question.
Thank you.
From non-deterministic it is moving to deterministic.
Yes. Yes.
Thank you, Professor. Like from neuroscience perspective, like I don't know whether it makes sense, but I was listening to a lecture by a psychiatrist. So he said that humans have a will, but that's not a free will. We have a will, but that's not completely free. I mean, like most of the processes are the unconscious mind decides, then comes, then after certain milliseconds we become conscious of it. So can you please explain that? I mean, I'm not clear of that.
Yeah, well, I mean, I cannot speak in the name of this neuroscientist, psychiatrist. But so as I see it, of course we are influenced by a lot of things that we have in our brain and our subconsciousness and so on, and just the temperature it is and everything. So we have a lot of influences, that's very clear. The question is really, do these influences completely determine us so that there is just only one possible future? So there's no choice at all? Or is it that all these influences that come and influence us, these boundary conditions, they of course restrict our possibilities a lot. But maybe there is still some structure with more than one possibilities. Think of this picture I had with the photon and the beam splitter. The photon cannot decide it goes these every possible directions. It is structure is forced to make only a choice between two possibilities. So it doesn't have infinitely many, it has two possibilities. And even these two possibilities come with very precise propensities. And he has only this choice. And I think in our case it's a bit similar. Out of everything you could imagine, most of the things are impossible. And you are conditioned not to make this and that choices, but still it doesn't mean, in my opinion, that there is only one possibility. There are still maybe a few possibilities. And sometimes, maybe not also all the time, but sometimes you really make a decision which is genuinely yours.
Okay, maybe the last question, gentleman over there.
Just in that, so I'm stuck with this photon phenomena. I don't know much of physics, but then could you please tell me when you are talking about the possibility that it might go left or right, not up and down, so that is like determined that it would either go left or right.
Yes, it is determined that you have two choices, not more.
Two choices.
Yeah.
But don't you think that the photon as something, as a characteristic, would have something that would probably determine the way it would go, you know, as in, for example, fire as a characteristic would burn itself and would burn others.
Yeah, I think I understand your question very well, and I think it's a very good question. This is really where you have to think again about this argument. If you have only one of these photon and one pair of possibilities, your intuition that maybe there's something hidden in the photon that actually says, no, this time you go left, this time you go right. But now if you have two of them, as in this example with the Berlin equality test, and you can make some little choices, so you can turn your beam splitter a bit. So you have these possibilities. And now you accept the idea that there's a real distance there, nothing jumps from one to the other, takes some time to go from one place to the other. And you also make the assumption that the choices of the settings, of the inputs, how you orient your beam splitter is independent of the photon. So it must have some independence. It's coming from this old movie or this archaeological site. Then from that, you can mathematically exclude the possibility of this hidden guiding information in the photon. The photon has really to behave intrinsically random, without any little guiding in it. It's very difficult to understand that. I'm not saying it's an easy thing, but and your intuition or your reaction shows that you have understood that there is something bizarre, but you have to go through this argument and convince yourself that there is just no way to avoid the conclusion that there is really intrinsic randomness.
Okay, thank you very much. So it's a very interesting, maybe Professor Nicolas, you can take a seat here now. Thank you so much. And it was indeed a great evening for all of us, learning a lot. And the Professor Nicolas, his skill, art, in bringing down the very complex concepts into our very mundane or the deities understanding of the language. So, and also thank you very much for all the questions. I know that there are so many present questions with you. So for sure, for us to get in here, we are very lucky. One, because of His Holiness the Dalai Lama convening this big conference, the Sikkim, and then I just got hold of the opportunity. I just took my chance whether or not Tibet House can organized program with him, and he so kindly accepted this. And later on also, Tibet House, we're thinking of the, say, organizing bigger, really proper conferences. Of course, earlier we had conferences on neuroscience and Buddhist psychology and the quantum physics and philosophy. So all these things have been ongoing programs. So as the moderator earlier said, that those of you who are interested in these programs, you can just send a letter to Tibet House, office@tibethouse.in, requesting to put you up in the mailing list of Tibet House, so that every week you will get the announcement and all these interesting programs. You can know about them, you can take part in them, and it becomes a sense that you are brilliant scientists. We can also include you as one of the presenters, participants. And then in one of those programs, we are again already made a request to Professor Nicolas to kindly accept this, and then of course he's very prominent and renowned scientist, so he hardly really gets time to come to India so often. So, but still he kindly accepted. He's saying he was saying that he has to somehow manage it with coincide with some of the programs. So that way, we are very lucky. So let us all give a big hand. Thank you so much, and to all of you, thank you so much for taking part in this program. And I see that many of the physics students are also here. And Professor Nicolas, I really like to make a very heartfelt request to you to come back again for such more conferences and talks. Thank you so much. And thank you one and all. Thank you so much. Thank you. Good night.